The final topic of Module 13 is definite integrals by substitution. Now this is rather significant topic in Calculus 2 and in Calculus 3 even more so, but here in Calculus 1 not very much, so we're going to treat it rather lightly here. The reason this is not very much of a deal is because of the fundamental theorem of calculus. Let's take this problem for instance. The definite integral of this function from y equals to 1 to y equals to 2, the signed area. How do we do that? We simply apply the fundamental theorem of calculus. Find out the antiderivative of this, or the indefinite integral, and plug in the top, y equals to 2, plug in the bottom, y equals to 1, subtract one from the other, and that's it. And we don't have to worry about plus c. It's pretty simple deal. All we have to do is to find out the antiderivative. Basically, that's solution 1. And majority of the students prefer this one. A slight majority, but majority nonetheless. Here we go. Substitution as a denominator, the derivative computation, and in the end, dy equals to this, the differential part. Substitute everything in and do appropriate simplification, and what do you get? You get a log function, and substituting everything, you get this antiderivative function. We don't need this plus c because the fundamental theorem says plug in the top, plug in the bottom, subtract one from the other. And when you subtract one from the other, this plus c minus another c cancel each other out. So we use just this expression, plug in y equals to 2, plug in y equals to 1, subtract one from the other, and what do you get? We get, well, this expression, and then this is numerical computation. So up to here, the exact same as, well, this very problem we already discussed in the second video, right? Exactly the same as before, and then plug in the top, plug in the bottom, subtract one from the other. It works well in Calculus 1, and there are some exceptions in Calc 2, but works okay. And in Calculus 3 or higher, now it'll begin to break down. So I have to tell you about the second method, and a little bit less than majority of the students prefers the second method. It's a little bit more elegant, a little bit shorter, and a little bit more powerful. Let's work this one out. This time we don't have to work out two integrals. Same substitution, and then we are plugging in, but before plugging in, let's work out the starting and ending point. Y is going from 1 to 2 as you see over here. Now y is equal to 1, plug in y equals to 1 to y squared plus 2y. What do you get? We get u equals to 3. Plug in y equals to 2, you get u equals to 8. So instead of going from y equals to 1 to 2, you're going to get u is 3 to 8. So you get the second line. And we don't really need the third substitution. You can simply calculate this u integral toward the end, and that's going to be it. Here's the next computation. Antiderivative, plug in the top, plug in the bottom, subtract one from the other, and then here's the numerical computation. We are not plugging in y equals to something. You're plugging u equals to something, so you don't really have to get y expression in the end. And this method is particularly useful when the final substitution is either impossible or too difficult to do. And that happens in Calc 2, not in Calc 1. The other problems, I'll just leave you. Now let's talk about some area computation problems. Here's one. Here's another. Related. And I hope everybody remembers the function. This is the very function we studied in the previous video. Okay, how do we set up the integral and then find out the area? This is a geometrical area, so if you simply set up the definite integral, it's a signed area, so you have to be a little bit careful about that. What am I talking about? If you set it up like this, area equals to the definite integral, x is going from -1 to +1, and then the integrand x1 minus x squared dx. This is not going to be right. the answer will turn out to be 0. You can clearly see from the picture. You have a symmetry, and then this is positive part and that's negative part. If you add them together, they cancel each other out, and the signed area will become 0. And this is meaningless computation because you have to find out the geometrical area of the shaded region. So what do? Instead of calculating the definite integral from here all the way over there, simply calculate area of this part going from 0 to 1 and then double it. Then of course this is not going to be 0, it's going to be something. And once you find this once you get this quantity, that's going to be the area that you're looking for. How do you get this? Well, find out the antiderivative and then plug in x equal to 0, plug in x equal to 1, subtract 1 from the other, the standard method. I'm going to leave you there. The same goes to this problem. This is going to be a little bit tougher because antiderivative computation is going to be a little bit tougher. You're going to get some residual x factor here, so you have to substitute those back in and do some work, just like we discussed in the third video. Basically, it's the very same problem that we discussed there, by the way. So I'll leave you there. And so much for module 13, and let's meet again in module 14.